So today we're going to cover Chapter 10, Section 1. Today we're going to learn about different lines and segments that intersect circles. So this lesson has a lot of vocabulary terms that you're going to need to memorize. So one thing that I might suggest that you should be doing is as you're going through this chapter, maybe start creating a study guide for yourself so you can remember all the terms. So the first thing we're going to do is define what a circle is. And a circle is the set of all points in a plane that are equidistant from a given point in that plane. And that given point is called the center. When we name our circles, we will be using that center point. Another part of a circle is a segment whose endpoints are the center and any point on the circle, and that is called a radius. Plural of radius is radii. So I'm going to go ahead and draw a circle. I'm going to add in the center point, and it can be named with any capital letter. It's any point in the middle of the circle. So this is the center point. It's point M. So when I go to name this circle, I can either write out the word circle and then put the center point, or just like we did with triangles, how we would draw a little picture of a triangle and then put the 3 vertices. You can also draw the picture of a circle. So draw a circle with a center point and then tell what that center point is. So these are 2 ways that I could name this circle that is pictured here. Now, for the other vocabulary term that's on this slide, the other term is the word radius. And a radius is just a segment that goes from the center to the edge of the circle. So it's to a point on the side of the circle. So let's say I said that this is point N. Radius is also indicated with a lowercase letter r. So let's say I told you that this radius of MN is got a length of 3. No matter where I draw in different radii in the circle, they will all have the same measure. So if I draw one over here, and let's say it's going to point X, this radii of MX would also have a length of 3. If I drew another one in another direction, this one would also equal 3. A radius is a segment. We need to reach back to our knowledge of Chapter 1. And remember, when you name a segment, you're putting a picture of a segment on top of the 2 points. So we have 3 different radii that I drew in here. And they all have the same measure, no matter where you draw them. So on this slide, we've got 4 more terms. The first one is a chord. Now, just like before, the radius is also a segment. So a radius is a segment, so is a chord, so is a diameter. These are all segments. So a radius, remember, went from the center to a point on the circle. A chord is going to be a segment whose endpoints are on the circle. So it's going to go from edge to edge. A diameter is a special chord. What's special about it is it has to go through the center point. Then the third one that's on this one is the secant. Notice the definition of a secant. It's a line that intersects the circle in 2 points. And then lastly, we have the tangent. Now, it's not the same tangent that we talked about in Chapter 9. This tangent is a line, and it's going to hit the circle or touch the circle at exactly 1 point. And that point where it touches the circle is called the point of tangency. Now, I know the next slide has a picture of all of this, but let me go ahead and draw one and walk you through. So let's draw a circle. Let me add in all these parts. So I'm going to go ahead and I'll name it the same center point that I did before. So this is circle M. Now if I draw a chord goes from edge to edge. So I could say this is A and B. So I could name this chord AB and then put the picture of the segment on top. Now, a radius, I saw this on the other slide. Remember, it goes from the center to a point on the side. So this could be MC. Then a diameter is a special chord, but what's special about it, it has to go through the center point. So if I go from edge to edge, but going right through point M, this is now a diameter. So this diameter, you could call it XY. And again, notice these three that I just drew in, they're segments. So the next one is going to be a secant. Get a different color here. I'm going to do the secant in orange. So the secant hits the circle at 2 points, and it's a line. So it's going to go through the circle, and I could call this DE. So the secant, DE, and it's got the picture of the line on top. And then the tangent, it's going to skim the side of the circle, and it's only going to hit it at 1 point. So I could draw a tangent here, and I could add another point here and maybe call it Z. So the tangent could be XZ, but the point of tangency would be point X. It's where it touches the circle. Now we're also going to see secant segments and tangent segments. But whenever they ask you to identify a secant or a tangent without the word secant, segment after it, then they're referring to a line. Because by definition, a secant is a line and a tangent is a line. So here is just a picture with everything that I just described in it. So we've got our chord, which goes from edge to edge. We've got our diameter, which needs to go through the center point. Still a chord, but what makes it special is it has to go through the center. And then we have our secant here, and notice it's hitting our circle at 2 points, and it's a line. And then we have our tangent line, which is going to just skim the side of the circle and only touch it at 1 point. And that 1 point where this tangent line hits it is called the point of tangency. So it says point O is the center of the circle, and it wants us to give the vocabulary term or the name of each figure. So let me go ahead and identify where OM is located. OM goes from the center to the side of the circle. So notice it's a segment, and that's what is pictured here. So this is, when it goes from the center to the side, this is called a radius. When it goes from edge to edge, and it's a segment, this is called a chord. Notice the picture on top of those capital letters was the picture or the symbol for segment, but notice in part C, they have now changed that symbol to a line. So when it becomes a line, and if we were to extend this now becomes a secant because it goes outside of the circle. Because remember, a line goes forever. And then MQ is from side to side or edge to edge, but notice this time it's going through the center point, which makes this a diameter. Technically, it's also a chord, but the better name is diameter when it goes through the center. ML is located over here. And notice the picture on top of the capital letters is the symbol for a segment. So notice it's only touching my circle at point M, making this a tangent, but because the picture on top of the capital letters M and L is the symbol for segment, this is a tangent segment. And we need to be able to identify this because we have a theorem coming up that will use tangent segments. Now notice, same letters for part F, however they changed the symbol to be the symbol for a line, which now makes it, when it's a line instead of a segment, making this just a tangent. And then point M is the point of tangency. It's where that tangent line is touching the circle. Now we also will see secant segments coming up later on in the chapter. But again, anytime they just give you the word secant or tangent when it doesn't include the word segment, they're referring to a line. Okay, so on this slide, they're asking us to distinguish between when it's a common internal versus a common external tangent line. So in order to distinguish between the difference, we need to draw a segment connecting the centers of the circle. So this won't be drawn in for you. You'll have to draw it yourself. So I'll put center points in each of my circles, and I'm going to draw a segment that connects them. Now, this segment that I'm drawing here is going to be what I use to test to see if my tangent is either inside, internal, or external. So in the picture on the left, they've drawn in a tangent. This line is tangent to the small circle and to the large circle. Notice it's only touching the circle at one point. When that tangent line does not intersect that segment that you draw in connecting the centers, this would be an example of a common external tangent. When it touches it, it's going to be a common internal tangent. Now, when you have two pictures of two circles that are side by side, I can actually draw in a second common external tangent, one that'll skim along the bottom. So this actually has two common external tangents. I cannot draw any more. This one's got a tangent line that is drawn in here for us. This is an example of a common internal tangent because once I drew in the tangent and it's hitting the little circle here and the big one here, it's crossing that segment that I drew in connecting the centers. So this is an example of a common internal tangent. And I can draw one the other way as well. So this one actually has two. This actually has a total of 4 common tangents. 2 are external and 2 are internal. Every picture, depending on how the circles are positioned, may have a different number of tangents. So you'll have to draw them in yourselves. So this is what I want to see in the homework is I want you to draw them in for the pictures provided. All right, so the next one is the definition of congruent circles. Congruent circles are just circles that have congruent radii. The second term here are concentric circles, and these are circles that lie in the same plane and have the same center. So this is like a real life example of concentric circles, could be like a bullseye or a dartboard. Now, congruent circles, they could be two separate circles. So I could draw two separate circles, and as long as they are labeled with the same radius length, so if I tell you this one has a radius of 3, and so does this one, then these are considered congruent circles. Now, they don't necessarily have to be two separate circles. The circles could overlap. So anytime you're just given that the circles have the same radius length, then you're going to know that they're going to be congruent circles. So let's say I draw one this way, and then I put another one maybe slicing through it. Maybe show it this way. And as long as I can show that this one maybe has a radius of 4, and then let's say the red one also has a radius of 4, these would also be congruent circles. Now, they're not concentric. They're not a circle on top of each other, but maybe one is flat and one is going sideways. When you have two tangent circles, they're going to be coplanar circles that are tangent to the same line at the same point. So notice how we have this little one and this larger one. It sort of looks like a snowman on its side. This would be the line of tangency. And notice they both share this same point of tangency. Now you could have a circle within a circle, and then this point of tangency would be right here. Now, these are not concentric circles. Notice they don't share the same center point, but they do share the same tangent line and the same point of tangency. This is our first theorem of chapter 10. Again, don't memorize the number. This actually has a name, and this theorem is called the tangent line to a circle theorem. So tangent line to a circle, or to circle. So we'll say to a circle theorem. And this one states that in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at the point of tangency. So notice here, AB is the radius, and then BC is the tangent, and these are always going to be perpendicular. If BC is a tangent line, then it's going to be perpendicular to the radius. So this is where we're going to bring back our chapter 9, because we're going to be turning this into a right triangle. I can go ahead and connect A to C, and notice now I've just formed a little teeny right triangle here. And if I ask you to find the length of AB, BC, or AC, I'm either going to use Pythagorean theorem, depending on the numbers, or depending on the numbers of the angle measures, I might also bring back my special right triangles, my 30, 60, 90, or my 45, 45, 90. So this is going to bring back chapter 9. Now, in the homework tonight, when you get to numbers 9 and 10, you're going to get a question, and they're going to ask you, is BC, or whatever the tangent letters are, is that segment or line tangent? What you're going to do is show me that the three numbers satisfy the Pythagorean theorem. because you need to show me that it forms a right triangle. So you're going to show me that a squared plus b squared equals c squared. If that's the case, then that segment or that line will be tangent, because it will be perpendicular because it's forming a right angle. All right, again, don't memorize the number. This one has a name. It's called the external tangent congruence theorem. So it's called the external tangent congruence theorem. I'm going to abbreviate theorem THM, so I'm running out of room there. Okay, and this theorem states that tangent segments from a common external point, and my common external point is point B here, are going to be congruent. So when you have two tangents, and I have tangent AB here and BC, when they both intersect or meet at a common external point, then I know that those two tangent segments will be congruent. And you can add a little wave to that equal sign. So AB is congruent to BC. This sort of looks like an ice cream cone or a snow cone. Okay, so for this example, one other piece of information that you need to be given is I'm going to give you that OT is a tangent. So OT is tangent to circle R. So because I've just given you the fact that this is a tangent, I know that a tangent and a radius, when they intersect, they're perpendicular. So I've got a little right angle there. I'm also going to add in the side lengths that they gave me. They gave me the length of OR to be 6, OT to be 8, and they want me to find the length of RT. So if you notice, RT is across from the right angle. It's my hypotenuse. So in order to find that length, I'm going to do a squared plus b squared equals c squared. Doesn't matter if the 6 is A or the 8 is A. You're just going to square them and add them, and that will give you your c squared. And then you'll square root it to get the length of RT. This happens to be a perfect square. If it was not a perfect square, you would leave it in simplest radical form. But the length of C, which is my RT, has a length of 10. Now, if you remember back to 9.1, when I covered this, I talked about some common Pythagorean triples. This is actually a common triple. It's a scaled up 3, 4, 5 triangle. That 3, 4, 5 triangle shows up a lot on SATs, PSATs. This one, they just took the 3, the 4, and the 5 and times them all by 2. So for part B, same picture. I'm going to label the given. So I'm given that angle OTR is 45. Now, same given, this OT is going to be tangent. So OT is tangent to circle R. All right, so now you can either recognize that this triangle now is a special right triangle, and this angle up here is also 45. If you didn't, you could add the two, the 90 and the 45, subtract from 180, and still get 45. Now, you can do this problem two different ways. You can either use your knowledge from section 9.2, that this is a special right triangle, and it's the 45, 45, and this side's going to be A square root 2, and they're giving me that OT here equals 4. So if OT equals 4, so does OR. And then RT is just going to take that 4 and put root 2 behind it. So honestly, the special right triangle is the fastest way. But let's say you forgot about the relationships of the sides. And you did recognize that this was an isosceles triangle. So if you recognize that you had two congruent base angles, then these sides are also congruent. And if they gave you this one to be 4 and this one to be 4, you could also do Pythagorean theorem. 4 squared. This is the other way, it's longer. And then this would give you c squared. 16 plus 16, get 32. Then you got to go back and do a factor tree. And you can do 4 and 8, you could do 2 and 16, whatever factors you want to start with. And then 4 and 4. Soon as I see I got a pair, I'm going to stop. I got a pair of 4s, 4 comes out, and notice it's the same answer I got that when I just used my special right triangle. All right, so for this one, they want me to name a line that is tangent to P, but not to O. Now, let me go ahead because the next two parts, B and C, also want me to identify external and internal. So let me add the segment that joins the centers. So P is the center point. So this is my segment that I get to see which tangent line crosses it. So a tangent line to P, but not O. So P's over here. And if you notice, if you draw in this tangent, this guy's tangent, and then if it goes into O, it's hitting it at 2 spots in O. So this would not be tangent to O, but it is tangent to circle P. So this answer is either going to be BO or OB. Doesn't matter the order of the letters. Now the external, remember that's the one that can't cross that blue line. So the external tangent would be down here at the bottom, CD. Because it's hitting at the point of tangency of C for circle O and D for circle P. So this would be CD or DC. Again, the order doesn't matter. And again, when they ask for a tangent and don't specify it's a segment, you need to put the picture of the line on top. And now the internal tangent would be this line going straight through here. It would be the AE because it's crossing the blue line. The point of tangency for O is A, and for P it would be the E. So AE or EA. All right, so for here, it says circle M and N are both tangent at point P. So over here is the point of tangency. And then PR and SR are tangents. So PR is here, and so is SR. These are tangent segments. Notice they're both meeting at the same common external point. So we learned a theorem that when two tangent segments meet at the same common external point, this tells me that PR is going to be congruent to the SR. So these are going to be congruent. The next piece of information that they gave me was that circle N has a diameter of 16. So if I draw in this diameter, let me draw it sideways here. This diameter is 16. The next piece they gave me was PQ is 3 and RQ is 12. Well, I can find the length of PR by adding 3 plus 12. So that's the answer to part C. And then remember SR is the same. So this one's also 15. So now the next piece they want me to find is PM. PM is this radius of the little circle. Now, what I can do here is since my diameter of the big circle is 16, I could draw a radius here from N to S, and this radius is going to be 8, 16 divided by 2, which is also another radius that I can draw over here from N to P. So which turns into be the diameter of the little circle. So this diameter is 8, making PM half of that. So this little piece here is actually going to be 4. Let me do that in black. So this is 4. Now MQ, it's not drawn in here. I'm going to draw it. It's right here. Remember, since P is a point of tangency, I've got a little right triangle here. And here's my classic 3, 4, 5. So MQ is 5. Now, if you didn't recognize that Pythagorean triple, you would do 3 squared plus 4 squared equals C squared, which is your MQ. 9 plus 16, 25, square root it, and that's how we get 5. Now for NS, I already answered that. That was this purple radius over here that I drew. So that's got a length of 8. And now NR does not have a segment drawn in there, so I'm going to draw one. NR goes from here to this external point. But remember, this S is a point of tangency. So I've got a right triangle here. This is another triple. It's actually the 8, 15, 17 triangle. So NR is 17. However, if you don't memorize your triples, you would have to do 8 squared plus 15 squared equals C squared, 64 plus 225. Add them, square root it, and that's how you get 17.